Swayam Prabha. Digital India. Educated India.
Okay, good morning. Following the discussion on cellulose, now we will go to the next big candidate in the space of biopolymers. We said that cellulose could be derived from various agricultural products. We saw sugarcane bagasse, rice husk, and various other agricultural products from which cellulose can be extracted. Starch is the next candidate, especially the thermoplastic starch. I'll talk about its source, composition, molecular structure, the properties, and what are the processing techniques, and which are the companies that are producing starch. I'm more inclined towards using recent research articles for discussing these topics because there are a lot of developments happening in the space of biopolymers. So textbooks have little older information. So I'm trying to get state-of-the-art information about these biopolymers. Okay, so many material that I'm going to cover in this lecture are taken from this green chemistry article. So you can refer to this article for more information. All right, so where do we get starch from? Okay, so basically there are plants which store starch as a energy reserve. Okay, so you can see them in cereals like corn, maize, wheat, rice, barley. These are all cereals that we consume as food, and that's actually very rich in we call them carbohydrate, but actually starch in particular. There are also many vegetables. There are root vegetables in which starch is stored as a root, cassava, tapioca, potato, beet, and so on. Right? Again, we consume them as food. There are also grain legumes like pea, lentils, chickpea, bean, etc. Okay, so the variety of plant-based source are available for as a starch, and there are many other agriculture waste or byproducts of agriculture practices that could also give starch-based sources. And starch is the second most abundantly available biopolymer. What's the first one? Cellulose. Okay, cellulose is the highly available because of wood and forestry and other plants, but starch is part of the plant in which the starch is stored. Okay. In terms of the chemical composition, just like cellulose, starch also is made up of sugars. Okay, so if you consider the native starch from the cereals and root vegetables, they are mostly semicrystalline. They contain broadly two important polymers. Okay, one is called this amylose, and another one is called amylopectin. Okay. So if you consider this amylose and amylopectin across various starch sources, amylose typically will have about 20 to 25%, and the remaining 75 to 80% are amylopectin. Okay, there will be few other things in different cereals. There may be a little protein, there could be a few other fiber and etc. But broadly, the carbohydrates are amylose and amylopectin, and largely amylopectin, and you can see that 1:4 ratio. So if you look at the amylose, this is amylose. So amylose have pretty much like a linear structure. They have this, you can see this how sugar units are bonded together through this glycosidic bond, and they can exist either as a linear polymer or as a helical structure. This is to do with the way the hydrogen bonding happens within the chain. Okay, so that can give a twist. So you can have this kind of helical or linear structure, and typically this amylose polymer would have a molecular weight of the order of 10⁶ Daltons. Okay, so these starch are very high molecular weight polymers. Whereas if you go to amylopectin, amylopectin are highly branched. Okay, so you can see that like amylose, there is this glycosidic bond that links the sugar molecules in the linear chain, but there are also other covalent bond between two chains. Okay, and that's what gives you branches and networking. Okay, so schematically one can show amylopectin to have some sort of a backbone with a lot of branching points because of this extra glycosidic bond, whereas amylose have pretty much like a linear structure. Okay, and there's no branching. So we are saying this amylose, this linear polymer consists of about 20% or 25%, and this branched amylopectin would have about 75 to 80%. And you can see the molecular weight. The molecular weight of amylopectin is 2 orders of magnitude higher. Okay, because of the branchingness and amorphous nature, the molecular weight of amylopectin is very high, about 10 power 8 Daltons. In terms of extracting starch, it's very simple. It's much simpler compared to how we extract cellulose. We saw in the case of cellulose, it is available with a mixture of cellulose, hemicellulose, lignin and silica. So you need to have alkali treatment, bleaching, acid hydrolysis, etc. But here on the other hand, a starch is pretty much available in nearly pure form in most of the cereals. So simple grinding and then dissolving it in water, getting a slurry and then getting into powder form is very simple. Okay, so the chemical process is very simple for extraction of starch. So now there are some general statement we can say about starch regardless of the origin. Okay, so whether we are talking about starch extraction from potato or from grains, the chemical composition can differ a little bit in terms of amylose and amylopectin composition. But broadly, you can say something about the characteristics of starch polymer. So they have an excellent film forming ability. Okay, that means you can dissolve it in a solvent like water and then cast into a film, dry the film, and you can remove this. And starch is a renewable source. That means you can always produce more plants, more starch can be produced. It can also be recycled, and also it's cheap, low cost. Okay, because it is dependent on the agriculture thing, so you can cultivate as much plant as you want and have a low cost production of starch. And the starch films are transparent and they have a good barrier property for carbon dioxide and O2, and that makes starch film an ideal or optimal candidate for food packaging applications. However, starch also is very hydrophilic. It will try to absorb moisture. It has a very poor water resistance, and as I said before, because of this glucose repeating units, and it tries to make high number of hydrogen bonds between the chain, across the chain. Okay, so interchain, intrachain hydrogen bondings are very strong in this, and that precisely makes this polymer brittle. Okay, and there is also a problem of thermal degradation and retrogradation of the native starch. So what we are saying, starch is composed of amylose and amylopectin. Okay, these are very high molecular weight polymers, and there exists a very strong hydrogen bonding which makes this material very brittle. Okay, so generally if you want to process this, we need to do what is called some sort of a modification. Okay, so starch modification is very important to be able to cast films or make some other products out of starch. So if you consider the modification types, there are something called plasticization, there are derivations, derivatizations, blending, and then something grafting of another polymer with this. Okay, so without this surface modification, the processability or the usability of starch is very limited. So what do we do with this surface modification? So if I have to say about plasticization, so plasticization is very important process for starch to be able to make into some sort of products. So plasticizers enhance the processability of starch. When I say processability, I mean you are able to mold into some shapes. You can treat this polymer thermoplastically, and then you can put into some shape. So what plasticization does? Well, plasticization changes the molecular structure of starch. For example, it leads to diffusion of water. The starch particle that expands, there is a gelatinization, that means the starch granule can disintegrate, and there could be a local melting of the polymer, right? These are the things that are possible. And what we intend to do with the plasticization is that it actually decreases the brittleness by increasing chain mobility. So why there is a reduced chain mobility in the native starch is because of the hydrogen bonds. Okay, there is a very strong hydrogen bond that makes the chains stiff. If the chains are stiff, the polymer is going to be brittle. If the polymer is brittle, processing is very difficult. So when you add a plasticizer, which is typically a small molecular weight chemicals, it will go and then disrupt the hydrogen bonds between the chain and make it a little bit more flexible. That means the chains, the polymer chains acquire more mobility, right? So therefore, we are able to improve the processability of starch at reasonably low temperatures. And if you look around the literature, what are the typical chemicals used as a plasticizer? These are very low molecular weight chemicals, something like water, glycerol, sorbitol, urea, formamide, ethanolamine, etc. Okay, these are all used as plasticizer. What these chemicals do? They go in between these chains and then compete for hydrogen bonding. These added chemicals would like to make hydrogen bonding with the chain, disrupting the chain-chain hydrogen bonding. Okay, so it's as simple as that. So because of this, as a plasticizer, what we want is, we want them to be hydrophilic, we want them to be compatible with the starch. That means it should be miscible, and then it should have a higher boiling point than the processing temperature of starch. When you process the starch polymer at high temperature, this plasticizer should not evaporate. It should not become volatile. Okay, so the question is to have a low molecular weight so that it can easily diffuse to the interior part of the polymer, and then it should compete for the hydrogen bonding. So it should be polar molecules. Then it should have a higher boiling points compared to the processing temperature. Okay, so that the plasticizer is intact and present inside the polymer matrix. I have given one example. So typically glycerol can be used up to some 20% weight. Okay, that means you will take 20 grams of glycerol, 80 grams of starch, and then when you mix it, you will make a starch composite that would be, I wouldn't call this a composite because it is not an additive. It is just a molecule that goes as a chain flexible inducer. Okay, and if you put too much of glycerol, you may see a phase separation. It may not be a homogeneous system anymore. Okay, so you can't put too less, you can't put too high. If you put too less, the brittleness will still be there. If you put too much, you may see a phase separation. You will have high polymer, low polymer concentration, phase separated states. Now, as I said, when we add water or glycerol as a plasticizer, typically you add 10 to 20%. That basically goes against the definition of bio-based polymers. We say bio-based polymers if it is 99% based on natural products. The moment you put 20% glycerol or 20% other things, then we say it is not bio-based. However, it is biodegradable as per the ASTM standards. Okay, it's compostable and therefore it is biodegradable under certain standard conditions. Right, and if you're wondering about plasticization is something very new, that is not. If you've ever made chapati, have you made chapati? How do you make chapati? You take wheat flour, what do? You put water. What do you put water? You are basically plasticizing wheat flour by adding water. Okay, and you should not add too much water. If you add too much water, the chapati won't come right. If you put too less water also, it's going to be very hard for you to make that into a chapati shape. Okay, so adding water in wheat flour and making chapati is nothing but plasticization of starch in wheat. Okay, so we are just doing the same thing. Instead of making chapati, we are actually making a plastic products or bioplastic products, as simple as that. So here is a kind of a molecular structure. What happens to the the plasticized starch? So as you can see, glycerol is basically CH2OH, CHOH, and CH2OH. So you can see that it has a lot of OH groups, right? And then you have something called sorbitol, and then you have the starch molecule, which is basically a repeating units of the glucose molecules. So you can see that once you put this glycerol, you can see this OH group of the glycerol will try to make hydrogen bonding with the OH group of the glucose, and you can see the more number of OH you have, more number of hydrogen bond it can make. So that means your plasticizer should have more number of OH groups, okay, so that it can disrupt the hydrogen bonds between the chain, because between the chains also the hydrogen bonding is between OH and OH. Okay, for example, if I take this starch, if I put another starch molecule, this OH group will interact with the other OH group of the other chain. Okay, so that's what the hydrogen bond between the OH and OH groups. So now putting a plasticizer, we are basically disrupting the hydrogen bond between the chain, and the molecule can go inside between the chain and then disrupt it. Okay, and that's what makes this chain a little bit more flexible. Okay, that means it becomes more processable. So we are converting a brittle material into a more flexible processable material. So here this example is for sorbitol. You can see there are more number of OH groups in sorbitol than glycerol. So you would expect sorbitol to be a better plasticizer than glycerol. Can you think of any other plasticizer with more OH groups? Okay, no answer. Okay, fine. So you can add ethylene glycol, right? Ethylene glycol is also another alkyl groups. Can we add lignin? Lignin also has a lot of OH groups. Can we add lignin? But lignin is aromatic. It won't be compatible with this. Okay, and it's also very large molecule. Okay, it has a lot of OH group, but it is hydrophobic, non-polar, because of the backbone is aromatic, and secondly it's very large molecule. We said plasticizer should be small molecules, more polar groups, more OH groups, and high boiling points. Okay, so this particular cartoon that you see here, that kind of summarizes the nature of interactions. Without these plasticizers, you will have a lot of hydrogen bonds between the chains. Okay, that's what makes them brittle. Once you put glycerol, sorbitol, and these plasticizers, the hydrogen bonds between the plasticizer and the chains will happen, and that's make these chains quite mobile and flexible. Okay, so that's the basis of plasticization. So now, just because we are able to plasticize doesn't mean that we can process it at high temperature and mold it into certain form. Okay, usually what happens is we add another polymer, another biopolymer or regular conventional polymer to be able to process it at high temperature. So generally for commercialization and industrial use, TPS blend systems are preferred. Okay, usually the starch with plasticizer is actually mixed with another polymer, it's certain proportion, then you can put it through various processing instruments, processes. And what we achieve by that is that the thermoplastic starch-based blend system can be matched to the properties of the regular conventional polymers. So what are the thermochemical process we are talking about? We are talking about extrusions, casting, melt blending, compression molding, all these process in which the material is heated to a high temperature and then it is put into a mold, or you do some sort of a change so that it acquire a particular shape. Okay, so all that is possible if you provide the plasticized starch along with another polymer. Okay, it's always a TS the starch blends. So if you look around the literature, you will see that starch is blended with either other bio-based polymers or petrochemical based polymers. For example, there are many studies in which PLA and starch are combined together to form a blend, and that can be extruded. Or you could also do that with polyhydroxybutyrate and vinylate. Okay, these are all other natural or bio-based polymers with which starch can be blended with. Or you have something called polycaprolactam or polyvinyl alcohol, this is polybutyl succinate, this is polypropylene carbonate. So these are all fossil fuel based, petroleum based polymers, and this can also be mixed with starch. So here is an example of comparison of mechanical properties between a commercially available thermoplastic and the petroleum based LDPE film. Okay, so we are trying to see that how good the thermoplastic starch is if I have to replace a LDPE application with a TPS. Can you give me an example of where LDPE is used? Where do we use LDPE? Give me one example. Polyethylene bag, yes. Single use polyethylene bag, milk packages, right? Food packages, food wrappings. Now suppose you say LDPE is not compostable, non-biodegradable, you want to replace it with a bio-based or biodegradable plastic, then this matter by is a commercially available thermoplastic starch blend. Okay, so here they are comparing with melt flow index, density, modulus, strength, and elongation at break. So you can see that the melt flow index, I have not defined what melt flow index is, but basically it means that you take a sample of a known weight, okay, and then you apply certain load, okay, and then heat the sample, and through an orifice you see over a period of 10 minutes how much polymer is coming out. It is basically an indirect measure of measuring viscosity. Okay, you can put into a real meter and find viscosity at high temperature, or you have a very simple instrument where you basically have a load cell and then you have a small capillary. So the material is packed here and then you put a weight load. Okay, usually this 2.16 gram is applied, 2.16 kg is applied on the top. Typically you take about 5 to 10 gram based on the standard, and then you heat this entire thing to a particular temperature. This temperature can be close to the melting temperature of the polymer. Okay, for example, in this case both materials are studied at the same temperature of 190 degrees Celsius. That means you can process the thermoplastic starch in the same instrument that processes LDPE. Same instrument, same temperature setting. You can see what is the melt flow index. So here when you say 3, it means when you look at when you take this material for 190 degrees Celsius and then you apply a load of 2.16 kilogram, you will see that 3 grams of this polymer will come in 10 minutes. Okay, whereas LDPE, depending upon the grade and source and molecular weight, the range is between 0.1 to 22. Okay, so there are LDPE polymer which will have only 0.1 gram in 10 minutes, that means very highly viscous, or there is another polymer which could be highly flowable or low viscous, that about 22 grams are coming in 10 minutes. Okay, so it kind of tells you viscosity. Then if you look at the density, clearly the density of TPS is higher because of the crystalline nature and packing, hydrogen bonds, and modulus, if you see, the modulus is actually much higher. So that means you have much more stronger polymer, and you can also see that tensile strength is also high, and the elongation at break is basically in the lower end of the thing. So what that means is, as long as you're going to use this polymer for some static application, like you make a bag or you make some sort of wrapper, this is fine. But then there are some other application where the film will be put into some very high speed roller mills. Okay, so in that case you want a very high elongation at break. Okay, in that case this may be not a suitable one. Okay, it may just tear in high speed roller machines at high shear. So this one having about 600%. What that means is you can actually extend 600% its original length before it actually tears. Okay, whereas this one you can only increase by 60%, then it will tear. So that means this polymer is a little bit more brittle and it breaks. Okay. So but in other conditions you can see that they are broadly comparable except the elongation at break. So the point is to look at various TPS, commercially available TPS and its properties, compare with what material that you want to replace from the existing application, so that you can see whether it's suitable or not. Right? And so what we have seen is only a blend with other polymer, but now there is also possible of making starch composites by adding fillers. Okay, for example, in this table you see that starch is produced from corn and it is actually mixed with the hemp fiber, okay, to make a composite. Starch with polyvinyl alcohol fiber, or starch based on maize with flax, starch from rice mixed with cotton. You can see many combinations. On one hand, you can draw starch from various sources. Then you have this reinforcement or natural fiber. Again, we have a list of library of various possible natural fibers, and then you have a lot of mix match composition. Mix match is possible. Okay, so here you can see that it is mixed with the clay and potato starch. So you can see there are many combinations. Cassava starch with jute fiber. Okay, there is an enormous number of combinations that is possible for you to kind of decide for a particular application. Now, whether you make the blend or the thermoplastic starch with other polymers or natural fibers, most of these are actually processable under conventional thermoprocessing units. For example, you can put this starch granules in an extruder. We know melt flow index, we know the temperature and all that. So then you basically make a melt of this, and this melt can be injection molded. Okay, so that means the molten polymer can be injected into a mold having a particular shape, intricate shape. In the previous class, we saw for the cellulose also that injection molding is possible to make some intricate shapes, right? So you put it into a mold and then you cool it, then the material will take the shape of the mold. Okay, or you can actually send this molten polymer through a slit if you want to draw a film. Okay, you can also make starch film through extrusion, and then you have set of rolls to collect it and then do roll to roll. And you can also add if you want to put any spray, you want to have some functionalization in the surface, you can spray your additional material if you want. Then there's other thing is something called blown film, where the molten polymer is actually blown through air medium. It forms a kind of a bubble, and then the bubble basically collapses here, and then you get a film out of this. So most of the carry bag that we see, starch film, are actually made from this blown film approach. So this is extrusion based. Then there is something called compression molding, as we saw before. Again, you have a mold, positive and negative mold, put your starch granule in the mold, and then you bring the mold together, keep it at a particular temperature, particular pressure as per the design. Then you basically get a final product that will resemble this mold that you have. Okay, or more simpler is to make a cast film. So you take a starch and then plasticizer, whatever you want to add, mix it, make an aqueous solution, right? And then you pour it into a flat surface, hot plate, and then you wait it for drying, and then you can peel off, get a film. Okay. The only thing is this is more like a batch process you have to do over and over, whereas this one is more continuous. So as much as the cellulose are processable under these processes, starch, thermoplastic starch and its blend are also made into this, can be made into this. So finally, this is a list of commercially available starch. You can see that this company Novamont is one of the largest producer based in Italy. The comparison I made here in this table, right? This table. So this matter by is actually sold by this company Novamont. So then there's Biologic, this is China, Hong Kong. So you can also see that where so Novamont produces starch, cellulose, vegetable oil, all that, and Biologic they use, I mean this is the product name, the pellet name. It is obtained from potato starch, how much they are producing per annum, all that is there. And Biotech from Germany. So you can see Germany, Japan, UK, Austria, there are many countries that are producing starch, because starch is one of the well known and the polymer that we have been using for food anyway. So okay, that's all I have. So we'll stop here.